So this is joint work with Salil Shram and Satish Rao. Salil should be around in Berkeley, definitely. It's the new and improved title from what I sent earlier, which is which will be part of the talk. I'll talk about sum of squares certificates for random tensor norms of random tensors. Independent of our work, the results on random tensors were also derived by, or very similar results were derived by Ewoing Lee, Vijay Bhattiporulu, and Venkat Guruswamy. Okay, so let me start by just fixing a CSP. So let's look at a very simple one. So random k-lim. So here I think of k as a constant, let's say k equal to 3. So here the model is, I just want to pick roughly m clauses. So let's say with probability m over n include an equation of the form so you have variables x1 through xn over the Boolean domain, and with probability m over n, for each I1 through ik with probability m over n, you sample this equation and include it into your system, m over n to the k, then you expect roughly expect to see roughly m equations. And here we'll be looking at a regime where this is sort of uninteresting for statistics and probability. It's very interesting in the regime where m is much larger than n. So you have much more than n equations. Think of m as n log n. So clearly in this regime there are no solutions. So there's nothing to study in terms of the solution space. So what are we doing here? Our goal here would be to, so in fact something stronger is true in this regime. In this regime, every assignment satisfies roughly half the equations. No assignment satisfies more than half the equations. So our goal will be to certify that in this given an instance from this distribution, we want to prove or certify that no assignment satisfies more than half the equations. So certify an upper bound on the number of equations satisfied by any assignment. Okay. So if this notion of certificate is a little bit confusing, you can instead think of a related model. Here the problem is distinguish between, so you have either a random k-lin instance, or I will give you an instance with a planted solution, a planted instance, where, so a planted instance is obtained by just fixing an assignment that you want to be the planted solution, and then each time you pick an equation, you make the equation consistent with this assignment with probability 0.9 and a random bit with the remaining probability. Okay. So you're given a system of equations. It's either a random instance, so you know assignment satisfies about more than half, or it's a planted instance where you're guaranteed that there is some assignment that actually satisfies 0.9 fraction of the constraints, and you want to say which is which. Okay? And essentially that's what, if you have an algorithm for that, you essentially have an algorithm for the certification problem and vice versa. So you can think of either of these as a problem. So what is known about this? So this is a fairly well-studied problem, right? And so if the number of equations is really large, So if the number of equations is n to the k over 2, okay, more than n to the k over 2, then there's a sequence of works which can actually distinguish between these two, or solve the certification problem using a spectral approach. So the spectral approach was, I think, initiated by Goethe and Krivulevich, and then I think for K-Lin, the latest work is by Allen, O'Donnell, Whitmer, and Barak and Moitra. So they can do this. So for example, if k equal to 3, if you have more than n to the 3/2 equations, then you can construct a matrix and compute its largest eigenvalue, and that will be a certificate that there's no good solution. In particular, in this case, you can distinguish between the two cases. Okay, and so nothing is known, no polytime algorithm known for m less than n to the k over 2. And in fact, it's believed that this problem is hard for m less than n to the k over 2. It's a sort of a very closely related to a cryptographic hardness assumption called learning with errors. It's also, this assumption has also recently been used to prove very strong, very beautiful hardness results for learning half spaces. So it's a really nice problem. And for me, I really like this problem because it's the easiest way I know to generate a really hard computational problem. You can just create a planted instance, and it's a really hard computational problem. You know the solution, but the other person doesn't. So it's a really and it's empirically also very hard computationally. So not just in the worst case. Okay, so what is our result? So our result is, of course, we don't get anything close to a polytime algorithm, but we show that if you use the sum of squares algorithm, you can strongly refute instance of random K-Lin in sub-exponential time. So in the following sense. So if you pick any delta, okay, if you give me or I'll just write the result, and maybe then there exists a degree n to the 1 minus delta sum of squares refutation or strong refutation if the number of equations m is bigger than n to the k over 2 minus 1 times 1 minus delta plus 1. So, but one way to think of this is the following. So if I just gave you linear number of clauses, if I gave you 100 n equations, we believe this problem is exponentially hard. If I gave you n to the k over 2 equations, there's a polytime algorithm, and what we get is exactly the linear interpolation between the two. So in 2 to the n to the delta time, you go 1 minus delta fraction of the gap between k over 2 and 1. Okay? So it's exactly the linear interpolation between the two. I'll say what the sum of squares refutation is. Just think of it as, you can also think of it as a spectral algorithm. We'll construct a matrix. We'll show that if you compute the eigenvalues of this matrix of size n 2 to the n to the 1 minus delta, it will certify that the value of the linear system is small. And this actually matches the SOS lower bound of Grigoriev and Schoenbeck. So Grigoriev and Schoenbeck both independently have showed lower bounds for sum of squares degree for refuting these instances, and this exactly matches that up to logarithmic factors.
So if I set in your thing delta equals 0, you get m that is n to the k over 2, right?
Yes.
And so you say that there exists a sum of square refutation that has degree.
Oh, yes. Oh, yes. Sorry. I switched in both places. Sorry. Yeah. Yeah. Right. Thanks. So it was yeah. If you set delta equal to 0, you should get the polytime algorithm. If you set delta equal to 1, you get a very dumb exponential time algorithm, and for every delta in between, you get. Okay, and so this is just for k-len, but you can ask the same question about other CSPs, in particular random k-sat or random any other CSP, and once you get a result for random k-len for all k, you can use a very well-known connection reduction to actually show that you get strong refutation for all CSPs. So basically, for all you get a similar result for all CSPs. So for 3-sat, for 3-sat you expect any assignment satisfy roughly 7/8 of the constraints, and what this shows is that if you have n to the 3½ clauses, you can certify in polytime and you get a n to the 3½ minus delta, you can certify in time to the n to the delta. Okay. Is it clear? Okay, so now that's good. So now so I guess in terms of running time, I should emphasize that if you have a degree d sum of squares refutation, you can find it in time 2 to the n to the d. So yeah, and so sorry, n to the d, just n to the d, and it's n to the d. So therefore you can yeah. So okay. So there's a related question which is for 3-len, and here the input, what you have is just a tensor. Okay, it's a k-dimensional array of numbers. So for this, for notational convenience, I'll actually use k equal to 4. So you have a 4-dimensional array of numbers, and you can think of this as a polynomial, and the injective tensor norm of the tensor is just the largest value of this polynomial in the unit ball. So this is the injective tensor norm, and the related problem here is, suppose I gave you a random tensor. Suppose T is a random plus minus 1 tensor. So every entry is IID plus minus 1. What you can use a simple union bound show that the injective tensor norm is at most square root n. Okay. For a random tensor with high probability, the concentration. So you know that if I generate a random tensor, the maximum of this polynomial is upper bounded by square root n. The question is, what can we efficiently certify? Okay. Meaning what upper bound, what is an upper bound that we can easily compute? It's always a correct on every instance, meaning on every tensor the upper bound should be should be at most, it should be at least it should be a valid upper bound on the spectral injective tensor norm, and on a reasonable fraction of random instances you want it to give you a good value. It's oh, sorry. I'm sorry. Yeah. Yeah. R to the n to the k. Thanks. Yeah, it's a k tensor which is a k-dimensional array of numbers, and each dimension is n. Okay, and here again you can look at a planted model where I take a vector v, look at v tensor k. Okay, so this is just a rank 1 tensor. Then I add random Gaussian noise to the entries. So it's a planted model, which is similar to the model here. And the question of certifying is exactly the same as distinguishing. This model is called the spike model, and Andre and others have studied this in the past. So here the question is, what's the best upper bound we can certify? Okay, and we obtain a similar trade-off result between the spectral and the exact upper bound. So for example, for k equal to 4, the actual value of the injective tensor norm is roughly square root n. But if you use, there is a spectral upper bound, which I'll just talk about soon. There's a spectral upper bound. I'll just denote it by this. We'll clear what this picture is. This is at roughly n. So this is something you can efficiently compute in polynomial time, and it will tell you that the values certifies the values at most n. And what we show is that you can get a trade-off exactly like this between these two numbers. So in time n to the delta, you can certify n to the 1 minus delta over 2. So it's exactly this. Okay. Looks like I'll finish quickly. Okay, it's good. Yeah, so most of the talk is really simple stuff. So please stop me if I'm unclear at any point. It's really very simple stuff. Okay, so for the rest of the talk, I'll actually just concentrate on this problem. Okay, so you have a random tensor, random 4 tensor, which has plus minus 1 IID entries, and you want to compute an upper bound on the value of this. Okay. Okay, so what's a natural way to compute upper bound? So firstly, we have this polynomial t of x is this. Okay. The one natural thing to do is, this is an n to the 4 tensor, n by n by n by n tensor. You can flatten it into an n squared by n squared matrix. So this is the same as, I can write this as a vector of length n squared sort of applied to this n squared by n squared matrix. Okay. Is it clear? And this notation, what I mean is, this tensor has 4 coordinates or 4 modes, I, j, k, l. And by this notation, I mean that I flattened this tensor into a matrix by actually taking the first 2 coordinates as one side and the other 2 coordinates to the other side. Okay? Okay, so this is just equality. So clearly this immediately implies that, okay, since x is a unit vector, if x is a unit vector, x tensor 2 is also a unit vector. So, or alternately, this is just at most the spectral norm for a unit vector x. This is at most the spectral norm of this matrix. Okay. So this just take the tensor, flatten it to n squared by n squared matrix, and you compute just the largest eigenvalue of the spectral norm of this matrix. It gives you an upper bound on the value of the polynomial t. Okay, this is the spectral algorithm, and note that this is just, what is this? This is just an n squared by n squared IID plus minus 1 matrix. Okay. and therefore its eigenvalues are roughly n, and you get that spectral bound. Okay, so we should do something different now. Okay, otherwise the talk will be over now. So what should we do? So what we'll do is we'll just take this thing and tensor every component and take the kth root. So let's just take this equation and tensor every component. So you get x tensor 2k, right? And then you take the tensor of this matrix. Okay, I'm using k for both. Yeah, this k is. Let's forget that this k was there. We're never going to deal with the k. We're always, for the rest of the talk, we're talking about 4 tensors, and we're going to use this because, or I could use a different thing here. That's fine. Okay. Okay, so I took the tensor product of this, every component of it. So then the number becomes the kth power of the number, and then I can take 1 over k. So this is exact equality so far. Okay, so now again, you could just say this is a unit vector, this is a unit vector, tensor powers of unit vectors. So this is at most the 10. You could say that this is the thing, but that would be sort of counterproductive, it would be useless. Because the spectral norms also tensor when you tensor. So this is useless. Okay? You could just upper bound with spectral norm of this matrix. But here's where we'll do something different. We'll say these vectors are not just arbitrary vectors. They are kth tensors of a vector in n dimensions. So a 2kth tensor of a vector in n dimensions. So therefore they have symmetries. So this is a vector in n to the 2k. Right? It's an n to the 2k long vector. But it has a lot of symmetry, because it has to come out of n-dimensional vector tensored k times. So in particular, if I permute, you can think of this vector itself as a 2k tensor. If I permute the coordinates of that 2k tensor, it stays the same. And the same is true here. Right? So since we are looking for vectors with these symmetries, we can apply those symmetries to the matrix. So here's what I mean. I mean that if I look at this equation, this is equal to the same thing the kth root. Okay, but now I've symmetrized the matrix in between by all the symmetries of the vector I'm looking for. So I can pick any permutation pi on 2k elements and any permutation sigma on 2k elements. These are the permutations of the coordinates, and I can apply that permutation to the matrix in between and average over all such permutations. So I'm going to average the matrix under these permutations. Okay, so I get a different matrix now, right? And the hope is that this will have a smaller spectral norm. Okay. So now I'm going to just upper bound this by the spectral norm of this averaged matrix.
Should be tensor k on the matrix, right? Just tensor k, not tensor 2k.
Yes. Thanks. So now this is my upper bound. This is the upper bound we're going to use, and we will actually we can first of all compute this upper bound easily in time n to the k by just taking the tensor and computing the spectral norm, and we'll prove that this is actually at most, in the case of 4 tensor, it's roughly n over It's roughly n over k, but today we'll just say n over k to the 0.1. Okay. So basically, you see that as I increase k, the amount of symmetrization, I get a better and better bound than the original thing which we had. Okay. So to make it more clear, let's just look at this matrix and see how its entries look like for k equal to 2. Okay, for k equal to 2, this matrix is let me call this M. So this matrix M is n to the 4 by n to the 4 matrix, okay, for k equal to 2. And if I look at its entry, suppose its entry, look at its entry A, B, C, D, comma, alpha, beta, gamma, delta. If I look at an entry like this, before symmetrization, it would just have this entry. T, A, B, alpha, beta times T, C, D, gamma, delta. This is the entry that you would have before symmetrization. What you have now is you'll have, for 1 over 4 factorial whole squared times every possible way in which you can match these things. So you can do T, A, B, alpha, gamma times T, C, D, beta, delta, and so on. So pictorially, there are 4 vertices, A, B, C, D. And then there are 4 vertices, alpha, beta, gamma, delta. And you draw whichever way you draw a 4 uniform hypergraph between the two sides, you will get one term here. So this is one term, and then you'll get a term like this. Sorry, maybe green. Yeah, for every possible hypergraph, you'll have a term. Or all sorts of. So that's the entries of this matrix. So there's polynomials in the entries of T. Entries of the matrix are polynomials, entries of T. But you can see that, see why this sort of a symmetrization should reduce the norm. Intuitively, what's going on is if it was a random tensor, these values don't correlate with each other. It won't obey these symmetries that the x has to obey. And therefore, this average, when you do this averaging, it will reduce the value. So it will reduce even entries go down, but in fact the spectral norm actually decreases. So that's the goal now. The goal now is to prove that if you take a random tensor and you compute this matrix, its spectral norm is small. Okay. Any questions so far? Okay. So we'll do the fairly straightforward approach to bounding the spectral norm. What's the straightforward approach is to just use trace method. So the idea is, okay, we want to upper bound the spectral norm of this matrix M. Okay, this matrix M, we want to upper bound its spectral norm. But since spectral norm is hard to get a handle on, we'll just use the expected trace of a high power of the matrix as a proxy. So, this is definitely upper bounded by this. And if you pick L to be like log n, or d log n in this case, or just say log n, much larger than log n, this is actually an approximate equality. Okay, so sorry, yes.
But it's 1 over 2L if you put m and transpose.
Oh yes, thanks. Yeah, this is 1 over 2. Yeah, thanks. Good. So it's really now the left hand side was hard to handle. The right hand side is still pretty complicated, but it's still just this is a polynomial. And we can compute expectations of polynomials easily. Okay, so our goal now would be to try to compute the expected trace of MM transpose altogether. Okay, so let's just unravel this expectation. Okay, firstly, just to get ourselves grounded, M is n to the 2k by n to the 2k matrix. Okay, just so that. So therefore, if you take this trace and you expand it out, it looks like, I pick the trace is going to be the sum over all possible cycles of length L of inside this matrix. If I take, and so this is a length L cycle. A length L cycle in MM transpose is product of L terms like MAI, BI, AI plus 1. So this picture is a way to think about it. So I have one term for every n to the, every choice of these sets from n to the 2k. So this is the expected trace. So of course I shouldn't lose the expectation. Okay. So now, okay, what's the main thing now? How does this look? Right, so now I can write this M itself as a polynomial in the T's. Right, every entry of M is a polynomial in the T's. Okay, so this entry of M is going to be a 4 uniform hypergraph, a random 4 uniform hypergraph between A and BI. So this is a very straightforward simplification. This is what happens. This is just going to be sum over all terms of this type. Okay. So what do? You first write down the So it's a sum over, you stack k tuples, 2 k tuples L times. Okay, that's a sum over that. And then once you stack the 2 k tuples, you pick a random hypergraph between them, and then you get a term for that. Okay, so this is all fairly straightforward, just that it looks a little bit more complicated when you write it out. But okay, so now this just becomes the probability that the hypergraph is even. So the key is that since each entry of the tensor is a random plus minus 1, when you take expectation, it only survives if every edge appears, if every edge appears an even number of times. So therefore, the only terms that survive here are those in which the hyperedges appear even number of times, and therefore this summation simplifies to this following calculation. So it's a sum over all tuples in n to the 2k. So you just stack vertices like this, and then you pick a random hyperedge, random hypergraph like this between the parts, and then you ask what's the probability that this hypergraph is even over the choice of these red edges. Right. Once I fix these vertices, these vertices are labeled with some numbers from 1 through n, and once you pick the red hyperedges, it will either turn out that every hyperedge appears an even number of times or not. Okay. and that gives you a probability that the hyperedge is even, hypergraph is even. And sum this over all possible assignments of vertices.
Every what is needed?
That every hypergraph, every hyperedge appears an even number of times.
So there are identities among the points in the
Right.
in
So
the
like
stacks.
A1 and B7 could have
Right.
some of the same vertices.
Okay.
So it's possible that a hyperedge can appear.
Yeah. So these vertices are labeled, right, from 1, 2, 7, 5, from elements in n. You have this picture. We have 2k, elements here, 2k elements here. You label the vertices from values in n, and then you pick a random hypergraph. And you look at the probability that every hyperedge appears an even number of times. And then you add it up, that's what you get. So this is what we need to bound now. Okay, it looks a bit nasty, but it's actually not that bad at all. So I don't know if I'll get to the end of this calculation, but I want to state open problems before I embark on this calculation. So I guess the most stark open problem here is we don't know how well you can approximate the norm of a tensor or even a random tensor. We don't have sum of squares lower bounds. We don't have computational lower bounds which are strong enough. For example, the following is still a possibility. I give you a random 4 tensor. In n to the log n time or n to the log squared n time, you can get a p-tas for its norm, which seems unlikely, but we don't know a hardness even in the worst case. Let's even the worst case. I give you a 4 tensor. Can you approximate its norm within one? You get a p-tas in time n to the log squared, and we can't rule this out. So it's a really it should be a really hard problem, but we don't have a good hardness for it. And it's related to many other things like 2 to 4 norm and computation and it's quantum 2-prover games, while approximating the value of quantum 2-prover games. So it's a very central problem for which we don't have good hardness.
Okay, so question.
Yes.
So why do you call these Nestor certificates?
It's a very good question. So this is actually just a spectral algorithm. You could say it's just a spectral algorithm. When you go to CSPs, you actually have to you have to sort of not look at this entire matrix, or at least we don't know how to prove it using this entire matrix. You have to pick a submatrix of this and compute its spectral norm. Because the key difference between CSPs and over here is, over here we have no normalization of the entries of X. So all the entries of X, the only normalization we have is that the total sum 2 norm is at most 1. In 3-lin, random 3-lin, we want all the entries to be within 1 minus 1. And for that, reason you need. So even over there, you could describe a spectral algorithm which just picks a submatrix of this matrix and computes a spectral norm. The reason to describe it as sum of squares is just for compactness, I guess. But
Sum of squares would find the best polynomial to upper bound the given polynomial. I mean, it is related. It's just like a.
Well, it is, but in the sense, but you could describe it easily just this way, just a compact way to describe the result. It's just a compact way to state the result. Right. Okay. Any other questions? So you really want me to get into this? No. Okay, I'll say at a high level how this unwieldy expression goes away. Okay, it's in 2 minutes. Okay, so it's really not that unwieldy. The idea is just that when you sample these hyperedges, let's not do it all at once. This seems a complicated process. Let's first sample a matching. between these parts. Let's just first sample edges between them before we sample hyperedges. These green edges. Then you could ask the question, what is this quantity? This quantity is actually, now you just sampled edges. So this is, if you look at random matrix theory, this is exactly the kind of things you count, and you can get very good estimates on this. Okay, so now the next step you do is you look at each layer, look at the edges, and you group them into hyperedges. You make red hyperedges by grouping these green edges. So, and then what you expect to happen is, even if the edges appear even number of times, because you're grouping randomly, the hyperedges won't be even with good probability. In fact, you know, if in a typical configuration, where every edge is even number of times, every edge appears roughly 2 times. So there's just a unique partner with whom, if you pair him up and create the hyperedge, it'll be even. Otherwise, it'll be bad. So the probability that the hypergraph is even, given that the edge is even, is really small, and you get a factor of 1 over k to the k, or to the L, because you have L such places here. Look. So this is it. So these two, this gives you exactly the bound that you'd get if you didn't do any averaging, and this helps you get an improvement over the bound, or that bound, which depends on k. It's exactly, if you take the kth root of this, you get k. Which is, questions? I think that's okay.
Questions?
How about Gaussian matrices?
Yeah, it works for Gaussian matrices also. Yeah. Yeah, but not in a clean way. We don't do it in the right way. We just say that if you pick a random Gaussian tensor, every entry is at most log n. That's not the right way to do it, but yeah, we do it.
For random CSPs, is it this? Does this upper bounding polynomial have the same form, like also the symmetrizing? Or?
Oh, the symmetrizing? Yeah, it's essentially the same. It's essentially the same. Just you have to pick a subpart of this matrix. The thing that goes wrong with random CSPs is the random variables are much worse behaved than plus minus 1. Here these are plus minus 1. You go to Gaussian, it's slightly ill behaved. But if you go to random CSPs, every entry is 0 with very high probability, 1 or plus minus 1 with a very low probability. So it's much less well behaved. So you have to actually worry about hyperedges appearing not just even number of times, but like 5 times gives you a much larger value than 1. The higher moments matter. Yeah, there's a hack to just look at the submatrix. There's a way to look at the submatrix to take care of that.
So, which submatrix?
It's just that you sort of want to avoid tuples where the same value appears too many times, because that sort of blows up the moment. Basically, suppose it's 1 on 1. Okay, then it's essentially all these hyperedges are either appear all together or all not. Sort of that's the event you want to avoid. So you actually look at a submatrix where this is multilinear, almost multilinear, meaning every label here, in every tuple, every label appears at most log n times. It's basically a typical, you want to just look at a typical tuple instead of a, yeah.
Other questions? Okay, great. Thank you.